Yo, what up? Welcome to Made by Ozzy. I'm Ozzy. So today we're just going to continue on with the project we started in the last video where we got our Cordis project all downloaded and set up a GitHub. If you haven't checked that one out, you should go back and get that one all set up and maybe sync the repo. Today we're going to write our first little bit of Verilog, and that's a hardware description language. Another one out there is called VHDL. It's a programming language to describe to the FPGA how to lay out hardware. So today we're going to write some to generate a timer. We want to make some of the LEDs on our little DE0-CV development kit blink. We're going to aim to make one that blinks with the 1 second period. That's half a second on, half a second off. And then we're going to try out, I'm going to show you a different way to do it too. That is, it's just a different way of doing it. Okay, so let's get started. Okay, the first thing we're going to do actually is to add the remaining push buttons and LEDs so that we just have them accessible in our project in the future. And so here's the QSF, and if you recall, last time we looked at it, it did not have these 4 lines at the bottom. These were added to it when we compiled the project. So that's just something interesting to know. Just going to go ahead and add the remaining keys here. So this reset N is something that's sort of interesting. You're going to see this pretty commonly on all FPGA programs. They have one master reset button, and it's pretty common practice that every module we write will have a sort of a reset condition that's going to be triggered by this signal. And notice it's inverted. That's what the little N stands for. It's actually active low, which means that by default we're always going to see voltage on that pin. And we want to react if there is ever no voltage. Just helps us catch a low voltage or no voltage situation. Okay, and now let's add the LEDs. Okay, that does the LEDs. Let's go add the clocks now. So here is the clock, and we really only need one. The reason that FPGAs provide 4 independent clock input banks is a topic we'll get into in the future to advance for right now. I'm going to go ahead and add all 4, but for the most part, we're only going to be using this first one, M9. Okay, done and added. So let's just, add into some text file. Not so bad. Dope. So let's go ahead and get these pins added into the Cordis project so that they're accessible to everything. Okay, to add the inputs and outputs, I actually want to kind of keep everything a little bit cleaner, so I'm going to start doing some organization here. So I'm going to start by drawing a rectangle to house all of my inputs. And so I got this input right here. And I have 3 other keys, I believe, and I could just hold control and drag it and it'll sort of create the next one for me. And I got 3, I believe. QSF would show me. Yep, okay, cool. And let me make one more copy here, but this one won't be named key, right? This one will be named reset N. Okay. And while I'm here, let me move these down and put the clock actually up top. Clock is normally one of the first ones. So again, hold control, click and drag, and go ahead and name it. I think it was clock 50. And I could just make a few copies of this. Fortunately, it increments it that way and not how I named it. If only. Alright, one more. Okay. Cool. Just give this a name while we're here. inputs. All right, now let's do the same thing for the outputs. Draw another rectangle. Totally matching. All right, we got this. Do the same little technique, click and drag. And I think I have 9. It went all the way to LDR 9. Yep. Okay. Go ahead and give that a name. Okay. And notice that it doesn't matter where physically on the schematic you draw things. When you connect them with this wire tool and the label on the wire tool. So everything's connected with labels. Be careful with that because it can lead to some real, spaghetti code, hard things to follow in the schematic type diagram. But it does make it pretty easy to work with in situations like this. All right, hit save. One thing I want to point out here is that the assembler and timing analysis have gone from green to this yellow now. This is telling you that changes have happened in this project here. And it generated a BDF. We still have our output file. We still have a working SOF. But if we load this onto the FPGA, we're going to get the behavior we had in the last video, which was this right there. And technically, the compilation of this project would be the same as what we have last time because all we did was add some I/O here. But it doesn't know that. All it knows is that it now has a different project than what it compiled last time. And if you want to actually run what you have here, you need to run the whole synthesis and compilation chain again. This key 0 has this little note showing which pin it's mapped to. And this LEDR0 has one, but none of the other ones have it. So you either want to remove it all or show it for all of them. So what you do is just right click, not on something, right click, show, and then show location assignments is on. So I've turned that off and now it's gone for all of them. And there it is for all of them. I'm actually going to turn them off because they just sort of get in the way for me. Okay. So I want to make an LED stay on for half a second and then off for half a second. So that basically means I'm making a square wave with a period of 1 second. So the only thing I really have to work with in the FPGA is this clock signal here, which I know is at 50 megahertz just off the datasheet. So one period of a 50 megahertz clock is 20 nanoseconds. The core way to make a timer based off this is just to count rising edges of your clock. Every time it goes from low to high, you're just going to increment a counter 1 time. And so how many times do we need to count a clock pulse in order to get 1 second for a 50 megahertz clock? Believe it or not, it's 50 million. So if we want to switch a state at the halfway point, we only need to count to 25 million. Okay, so now that we got all this setup stuff out of the way, let's make our first Verilog module. So come over here, File, New, Verilog HDL file, and it opens up a text editor. Okay, so this is going to be a module, so we actually started with the keyword module. Now we have to decide on a name. And it can't start with a number, so I'm just going to name it what it is. 1 second period pulse. And then we have to define all the signals, both the inputs and outputs to this module. So we're going to have 2 inputs, a clock and a reset signal. Then we're going to have 1 output, just an output, and then terminate it with a semicolon. And module always looks for keyword and module. So to make sure I don't forget, I'm just going to put that down there. Okay. So notice we didn't actually define what the inputs and outputs were. We put them in order, but Verilog doesn't know that. Here in the body of the module, we need to now define the inputs and outputs. And those are just with the keywords: input clock, input reset, and then output out. So let's take a quick second to talk about data types in FPGAs and Verilog. There are only 2 data types wire and a register. And by default, all these right now are set up as a wire, which is the same thing as what we got here. The difference between a wire and a register is that a wire can change at any point in time. There is no restriction. So here, whenever we press key 0, it's going to switch the state of LEDR 0, as opposed to a register where it will actually save a state for some time. Usually that's used along with the clock signal to save a state for one entire clock period. Not necessarily a clock though. I mean, usually it is, but it doesn't have to be. But in order to make this, I'm going to make this output here a register instead of a wire. And I do that by just adding the keyword here, reg. Okay. Now what else do we need for this module? We're going to need an integer to keep track of our count. We want to count to half a second using a 50 megahertz clock pulse. So that means we need to count to 25 million. So in something like C++, you would do something like int count equals 0 to instantiate your variable. We don't have that in FPGAs, right? We only have wires and registers. So what we're actually going to do is we're going to create a register, and we're going to tell it how big of a register that is, how many bits it is. So if you're going to do something like C++ with a 32-bit integer, you would actually define 31 to 0, that says it's 32 bits, and then give it a name, count. So this actually brings up an FPGA design philosophy that let's just get out of the way right now. We're not going to settle for just 32 bits or 64 bits for integers. In general, we're always going to try to minimize the number of bits that we are using for any given thing. So we know we need to count up to 25 million because we have a 50 megahertz clock, so we want to count half a second. So we need to count up to 25 million. So how many bits do we need to store 25 million? So we just need to convert to base 2. That's a pretty common function. We're going to actually use log with base 2 for 25 million is 24.57 something. Round up, we need 25 bits. So if we need 25 bits, I'm going to declare the address range as 24 to 0 to give me 25 bits. And we could give it a little comment, 25-bit integer to count up to 25 million, 25 million with 50 megahertz clock equals 0.5 seconds. Okay, good. Cool, so now that we have our inputs, outputs, and variables that we need to use, they're already set up, let's go ahead and define our logic. And how we're going to do that is we want the FPGA to do something every time it sees a rising edge of this clock input. So you do that by specifying with the keyword always and tell it something to look for. And in this case, it's always going to look for the positive edge of that clock signal. Okay, and this has the keywords begin and end to capture everything that's going to happen whenever this condition is true. This is a lot like in C++, you'd have a main and then brackets. It's a lot like it, but instead of brackets, you have the keywords begin and end, and instead of main, you have this condition. Do something on this condition. So what are we going to do? The first thing we're going to do is actually, well, to be clean, I'm going to give myself notes of what the end is correlated to. First thing we're going to do is we're actually going to declare a default condition that's going to happen whenever our reset signal is not what we expect it to be. And we expect reset to be high all the time because it's active low. So we're going to look for if it's ever not high. If reset, then we're going to do something. And again, I'm going to capture all that. So if not reset, because the user pressed the reset button or there's a power drop or something, we're just going to reset everything. So we're going to reset count to 0, and then we're also going to reset our output to 0. Okay, cool, easy. Now, assuming reset is high, like we want it to be, then now we got other logic to do. Else begin and else reset. So first thing we're going to do is we actually need to check the state of our count, and that's going to dictate what happens. So if count is greater than 25 million, 1, 2, 3, 4, 5, 6, then we're going to do something, right? Count. Otherwise, we're going to do something else. Okay, some space, make this a little cleaner. Okay, so if count is over 25 million, we need to do two things. We actually need to change the state of our output, and that's with this assignment. Note this, I'm using the less than sign and an equal as opposed to just using the equal sign. Using the equal sign does work, but it does do something physically different. So we'll get into that in the future, but for now we'll be predominantly using this one, that type of assignment operator. So we're just going to change the state of it. Whatever it was, change the opposite. And we're also going to reset our count back to 0. Okay. And if it's not yet 25 million, then the only thing we need to do is increment it. Count equals count plus 1. Easy. Okay. That should do it. That's it. This is our first Verilog module. This should change the state of our output out whenever count hits over 25 million. And because we know the timing of this clock signal, that should be every half a second. Okay, so let's go ahead and save it. And I'm going to create another folder in the repo here called library to hold all these modules that we're going to write. Wow. Okay. Oh, some fudgy fingers on my part. Okay, and we're just going to name it what it's named. 1 second period pulse. Okay, great. Now I have this Verilog module, but I have this schematic diagram top level file. So how do I use this Verilog that I just wrote in my top level schematic diagram? And the answer is I need to turn this Verilog into a symbol, which I could use on a schematic, much like this guy. So come over here, and I'm going to press File, Create Update, Create Symbol for Current File. And it's going to go ahead and it's actually going to try and compile that file to make sure all my logic is correct. And I say compile really, but I really should just say synthesis. It doesn't do the whole thing. All it does is check the logic. And if the logic is cool, then it's cool. And so we created this .v file, that's for Verilog, and then running that create symbol created this here, this .bsf file. And I'm just going to move this into library so we can keep it clean. Okay, now if I want to use that in my top level here, I need to drop in a new symbol. So I go to here to symbol tool, and I need to actually search for it. And so that's going to be here in the repo that we just made in library. And here's the BSF file. So I'm going to open it. And that's what it looks like. It has the clock and the reset input. It has an output. Okay. So drop an instance of it there. And let's go ahead and tie these to some physical signals. Okay, so I'm going to go ahead and draw a wire for each signal. So using this little tool here, drop a wire right there. Drop another one for reset here, and then one more for out. And then, so we're going to tie this one to clock 50. That's the clock we're going to use. So just click and type clock 50. And then for reset, it's a reset N. So I'll type reset N. And then for the output, let's tie it to LEDR1 because we're already using up 0 over there. So LEDR1. Okay. Cool, awesome. Save, and let's hit compile. Dope, all right. Compilation was successful. All right, so okay, it's all compiled. Let's go ahead and program it onto our board. So we come over here to tools. Let's open up the programmer. Okay. Picked up our USB blaster. It's looking at the SOF, which should be the updated one because we just compiled. So let's click start. And let's go check out if it actually worked. Okay, so there's our board programmed, and it looks like it's working. The second light is blinking. The first light is still triggering depending on our button. Okay, everything's looking great. Cool. So now that we've got a timer working off of counting pulses up to a certain threshold that we calculate, I want to talk about a different way of doing a timer that is real quick and easy, requires very little logic hardware to execute, and that is simply by using the bits in a counter. You still use a counter, but instead of having to check against the threshold, you could just look at the bits individually of that counter. So, for example, if we had a 4-bit counter counting clock pulses, the 0th bit would basically be a square wave at with double the period of what the clock is. Then the first bit or bit 1, I'm sorry, would be double the period there. Bit 2 would be double the period of bit 1, so on and so forth. Eventually, with the 50 megahertz clock, if you just kind of keep going at bit 25, now you have a period of about a second. At bit 26, about 2 seconds. Bit 27, about 5 seconds. So if you're willing to make some concessions about the exact period of your switching, time, then you could get a little blinking light or a timer working really easily and quickly with very little logic. Okay, so let's get a general purpose counter working that we could use as a timer. So let's go to File, New, another Verilog file, and it's going to be another module. And let's just name this general. And how many bits do we actually want? I guess we're going to want 27 to get all the way to 5-second period. So 27-bit counter, and we're going to have the same inputs, clock, reset. Our output is going to be different though. It's just going to be the whole counter. Terminate that, make some space and add that end module. Okay, let's define the inputs, input clock, and you can actually put them on the same line like this. Now the counter is going to be a little bit different. So it's also going to be a reg, but it's not, I'm sorry, okay, my keyword's wrong. Output, reg, and it's going to be the counter, but it's not going to be 1 bit wide like this. It's actually going to be 27 bits wide. It's a 27-bit vector, or array is the terms used. So to make 27 bits, we specify from 26 to 0, counter. Okay, cool. So this one, we're going to do the same sort of thing where it's going to look for the rising edges of that clock again. So always at positive edge of that clock. Begin, end. Okay. Always. Give myself some space. Again, the default reset condition. This is going to be really commonplace. Almost every module we write is going to have a default on reset. And this is just going to reset counter to 0. Okay. And then if it's not on reset, all we're going to do is increment counter. Okay. That's it. We're done. Let's save it. Not in output files, save it in library. Give it the name there. General 27-bit counter. Okay, perfect. And let's go ahead and create the symbol for this one as well. So File, Create, New Symbol. It's going to try and compile it. Great, compile successful. And then let's go ahead and drop, I'm going to move this over just so we have some room. Let's drop it in here. So a new icon. It's going to be in, oh, you know what? I didn't move it into library. So let's come over here. There it is. Move it into our library. Now I should be able to find it pretty easily. Oh, well. There it is. Okay. Again, clock, reset, and a counter. Okay, oops. Didn't mean to drop multiple instances. Okay, so let's see if I can just copy these and reuse them. Control C, Control V, Control V. Perfect. Okay, and notice this one is a thicker line than these because it's actual bus. Um, and it's thicker. So I'm going to give it a generic name. This is sort of like creating a local variable. It's not directly tied to an input or an output. So let's just name it that. Local counter. Easy. It's like I created a brand new one. And now what I'm going to do is I'm going to tie the individual bits from this counter to some LEDs. So I'm going to go ahead and copy this wire, make a few more instances of it. So, okay. And then this one, I'll drop a wire left and right. Okay, so this one you could guess we're going to tie it to an LED. So let's go ahead and do that. LEDR2, we're already using 0 and 1. What is this side going to be? So right here we have a local variable, local counter, which is actually an array of 27 bits, and we want just one of them. So how do we get a single bit out of this bus? Well, two things. Actually, I forgot that I need to use this syntax. I need to specify the entire bus all at once, and I know it's from 26 to 0. Actually, in hindsight, that should have been 27. Okay, looks like we don't have that bus there. But from 26 to 0, specify it with that, the dot dot. And then I can actually just call the specific bit I want. Local counter, and let's do the biggest one, 26. And this will just call the 26th bit from that bus local counter. This is really a blessing and a curse, because if you're in the habit of using numbers at the ends of your variable names, a lot like key 0, key 1 here, it could really trip you up pretty quickly if you're not careful and consistent about what is a bus and what is a single wire. So that's something to keep track of. It's convenient when you're calling it like this, but can really screw you up if you don't watch it otherwise. So let's do this for the two smaller ones too. So Control C, Control V, another one right there, and one more. Okay. And this one I'll write to LEDR3, and then LEDR4, and let's look at one bit less. So that was bit 26. Let's look at bit 25, and then bit 24. Okay, so that should do it. This should compile, and this should let us see 3 different LEDs, all at blinking at different rates. They see half as much as each other. So let's hit compile and see what happens. Yes, save everything. All right, dope. It's all compiled. Let's go ahead and open up the programmer again. All right, this should all be updated, and let's go ahead and write it out to the FPGA again. Dope. Let's go see if it works. Okay, great. Yeah, you could definitely see that the LEDR2, which is the third one, is definitely has the slowest period out of all of them. And the two next to it basically have half the period and going in order, exactly as we expected. All right, great. Another working project. So the last thing we need to test is to see if our reset default condition actually works. So I'm going to go ahead and press reset, and all the buttons should turn off, except for that first one, which is still tied to this because we never integrated any sort of reset logic. And then once I let go of reset, all the lights should start up again. All right, dope, cool. We know that's working. Okay, got all that stuff done. So I'm just gonna go ahead and save that CDF when I close that. Yeah. And then just gonna go ahead and close Cordis and push everything. Okay, every time I every time I build a new project in Cordis, it generates a whole ton of files. I'm gonna have to clean up the git ignore at some point. I'm sure some of these I could ignore. I'm not sure what it is. So right now I'm just gonna stage them all. Added timer modules and go ahead and push it. And today is actually Wednesday, and probably not gonna have this video up until Saturday, so it's up a little early on GitHub if you're checking out the GitHub. All right, cool. That was a lot of fun. Verilog's not. There's nothing too tricky about it. Nothing too scary there. We're gonna obviously build a lot more complicated modules as we continue working on this project. A reminder again, this whole project we're working towards, we're gonna turn this DE0-CV into a crypto miner, mining the odocrypt algorithm on Digibyte, and then we're also going to turn it into a graphics rendering piece of hardware like a GPU, and try to implement the OpenGL standard functions in Verilog, basically. So in the next episode, we're going to go ahead and add all the pins for the 7-segment displays and get something working to control all of that. Okay, I'll see you guys next time. Thank you for joining me. So just a friendly reminder that I did make madebyozzy.com for a quick reference for things, the GitHub, the user manual, if you want to contact me. And then, of course, if you like the content and you feel like helping me out and contributing, you could find all of my crypto receive addresses.